Welcome to Photonic Integrated Circuits Enabling Quantum. I'm going to ask my panelists to introduce themselves just briefly. William, Jen, and Chris.
Okay, I guess I'll start first. I lived mostly in the Northeast, did my schooling in Massachusetts, went out to NIST Boulder, worked a couple of years with some really good people. And now I'm at MIT Lincoln Laboratory. I mostly research on using photonics for to do things that normally it can't be done in using the traditional means. Right now I'm developing narrow linewidth lasers for portable optical atomic clocks, but also I'm interested in generating ultra-stable microwaves from photonics, or making filters that aren't realizable using traditional microwave means.
Great. Jen?
Yeah. Well, thanks for the invitation, Mark. Yeah, my name is Jennifer Black, and I am recently joining industrial R&D. I work for Vescent Technologies. Before that, I worked at NIST in Boulder also for a number of years as a postdoc and a staff scientist. And before that, I did my PhD in the University of California, Santa Cruz. And the common thread of the research I've been doing is with photonic integrated circuits for various applications, most recently for nonlinear photonics to produce fun colors for quantum, and working on PIC platforms, hopefully to enable future technologies.
Great. Chris?
Yeah, and I'm Chris DeRose from Sandia National Laboratories. And I've been working on PICs for about 20 years now, which is kind of hard to believe. But I started out in grad school working on optical modulators, doing hands-on work in a clean room, actually fabricating these devices. And then I went on to Sandia National Laboratories as a postdoc. And what really drew me to Sandia was the fact that we had professionally staffed around 65,000 square feet of clean room facilities, both a CMOS fab and a 3.5 compound semiconductor facility. And I wouldn't have to do fab anymore, and I was really excited about that. And so I went on as a postdoc and did research in silicon photonics and stayed on as a staff scientist for about 10 years before doing a stint in industry at a fabless company, but still doing photonic integrated circuit work. And so I've got experience working with external fabs. And in the last 4 years, I've gone back to Sandia as an R&D manager, managing a group doing quantum computing with trapped ions. And so now I've got about 4 years of experience working with the staff on developing photonic integrated circuits for quantum applications as part of my job. Yeah, so it's been exciting.
Great. Thanks. Thanks, everyone. So a little bit of background, right? So just to put everybody on the same page, photonic integrated circuits have really come to commercialization in datacom and telecom at 1550 nanometers, that sort of thing, but they haven't really addressed some of the many challenges that come with applying them in a quantum application. And so, however, to address that, the government governments around the world basically, but in the US, the CHIPS Act, DARPA, and some other programs, as well as recently Department of Commerce has funded Elevate Quantum to sort of address these things. And with that background, I wanted to ask, start with William here. Where do you see this funding helping most to support so far the ecosystem, and what do you see as the remaining gaps, technically, physics problems, that sort of thing? What comes to mind for you?
Yeah. So what I'll say is that I'll say absolutely is needed to fund PIC development for quantum. A lot of these quantum systems are large, and the only hope that you have for bringing it out of the laboratory is to actually scale down very dense elements onto a PIC. So it's actually pretty crucial to fund these things. So far, in terms of the funding I've seen, some of it has been on optical clock work, trying to make portable optical atomic clocks that one day might fly in the sky. A lot of it's been on frequency combs, microresonant frequency combs, things to shrink it down onto a chip that can take something from a system scale originally and try to make it small and put more functionality on there. Now, in terms of stopgaps, I think there's a lot of things to work on. Quantum itself is pretty challenging. Unlike the telecom wavelengths at 1550 nanometers, once you get into the visible, everything gets a lot harder to do. The reason is because there's a lambda to the 4 famous Rayleigh scaling. Your loss goes up to the 4th power with wavelength, all right? And then things get smaller.
As you go shorter wavelengths.
As you go to shorter wavelengths.
Yeah, it's just a killer. Yeah.
Yeah, exactly. And you need these visible wavelengths for quantum. You also, as things get smaller wavelengths, they get more tightly confined. That can help you in certain things, increase your intensity, but it can also hurt you. Your alignment becomes crucial, right? Small changes in fab variations are very tough to control. So I would say scaling to the visible wavelengths is pretty tough. Making a high extinction ratio modulator, or AOM, those don't exist on chip right now. You need something like 80 dB extinction for a lot of these quantum applications.
Yep. Jen.
Yep. Yeah, so a lot of the funding, as William pointed out, has been supporting fundamental research and development, a lot of interesting physics, exploring new techniques, and quantum especially has pushed these technologies sort of from telecom, longer wavelengths, to bluer wavelengths. And that's a real challenge. Even if we fundamentally know how to make these devices, making them reliably with low loss for the requirements of quantum is a real challenge. And a lot of these funds are for universities, user facilities, small scale fab for rapid R&D for prototyping. But to really commercialize these types of devices, see them go out into the world, you mentioned like clocks, for example, optical atomic clocks. There's really a gap in how you create these devices reliably at scale and really see them go out into the world.
Chris?
Yeah, I'd say whenever you hear someone give a talk about PICs and what the vision of a PIC-based quantum system is, the kind of canonical thing that you'll see in the talk is a picture of a messy optics table with lots of mirrors and saying, how are we going to get rid of this stuff? We're going to put it on a chip. We're going to do that with PICs. But I think so far the things that funding have helped with the most, in my opinion, are kind of individual component level and maybe small subsystems. So just a couple examples of things that we've been involved with recently. One is a laser system for rubidium-based atom interferometer. And so in that case, we worked at 1560 nanometers. So rubidium conveniently has a transition at around 780 nanometers. If you double that, it's around 1560. And so we could work with our telecom-based components, and so can leverage all that ecosystem that's already been built up. But then you need some nonlinear optics as well to double it down to the rubidium and making that efficient at a chip scale. Was one thing, so a small subsystem of a bigger atom interferometer. And then the second is DARPA had a program called APHI, which was atomic photonic integration. And so as part of that, Sandia was one of the performers, and we were developing a ytterbium-based ion clock. And we developed a lot of the sub-elements of that physics package, one being single photon avalanche detectors monolithically integrated into an ion trap, and low loss, ultra low loss waveguides in the UV to visible. As William pointed out, a lot of these atom-based systems require non-conventional wavelengths, and so we were ranging from around 370 nanometers up to around 700 nanometers with those chips.
Great. And, in my interactions with Lincoln Lab and Sandia, it's really, and some of the quantum computing companies I'm talking to that are working with both your facilities, you're on the front lines of advancing this tech, and you're doing many things for U.S. government customers that are really on the leading edge. How do companies best partner, work with Sandia and Lincoln, because you're able to work in an R&D capacity, I understand, but you're not really allowed to scale that commercially for the ecosystem. So how do companies work with you? What does that look like? And let's start with you, Chris.
Well, yeah, so we have a number of different ways to work with companies. One of, I guess, our charters as a national lab is not to compete with industry. And so whenever we're working with a company, we want to bring something unique to the table. And so oftentimes it's some capability that we have at our lab that isn't commercially accessible easily. And so we can partner with companies through joint proposal writing to the government. We can also do things called CRADAs, which are collaborative R&D agreements. And so oftentimes companies will just have internal funds, and we can take those funds and then do a joint R&D activity with a company. We can't lead things like SBIRs, but we can be subcontractors to companies through SBIR type programs as well. Those are some of the, I guess, most common ways that we work.
Great, and then William?
Yeah, I think our MIT Lincoln Laboratory functions pretty similarly. We mostly work on SBIRs and STTRs with commercial companies. We also can actually submit to programs, for instance, DARPA programs with them, and if we get a role, then that can also take place. We have internal funding to work with outside institutions. Mostly that has been academia, but I think, in principle, anything, you can put anything as your joint partner in that.
Yeah, great. And then Jen, from the commercial side, how do you look at partnering with, say, a Lincoln and a Sandia, and then also, how do you scale this?
Yeah. I think both you guys mentioned sort of the primary vehicles. I was also at NIST for a long time, and we worked with small businesses through CRADAs and SBIRs and also DARPA programs. And so that's, I think, the primary vehicle for cooperating between federal labs and companies. But if you, say, develop a technology through one of those agreements, that lab may not be able to fabricate it for you at scale to commercialize. And so that leaves, a problem for the company, right? So maybe you develop some technology you'd like to commercialize, put into a product, but who then fabricates it, and can they do that at scale, that the company needs? So those are the primary vehicles. I think a lot of people are working with one another, both at universities and federal labs and companies. But how we as a community, realize some of these advanced technologies and see them go to market and really capitalize on all that research that we've invested in is a real challenge. Things like the CHIPS Act and have funded things like microelectronics commons, and Vescent Technologies is part of Elevate Quantum, and I'm really excited to see what will come out of that, including incubators and also fabrication facilities. We could talk more of that if we like. I don't.
So let's roll right into that and then probe a little deeper, right? So some of the big foundries, commercial foundries, global foundries, that sort of they'll listen to you if you bring pots of money, large pots of money. But if you're a smaller company doing a multi-project wafer run or development, it's probably, chirping birds. You're not going to get a lot of interest there, right? At least that's the feedback that I've heard. So, how do you deal with that? So like if you say you work with a Sandia or a Lincoln Lab to sort of progress to the state of the art of photonic picks, and then you work your CRADA, you do your stuff, then you're going to build this. So you said university fabs, you said Elevate, so what does that look like? How does that work?
So at real prototyping, basic R&D level, it looks like maybe a university owns a fab, and you can work with them or maybe place someone in that fab to do the prototyping. Beyond that, there are some companies that offer, like you mentioned, multi-project wafers, and so you get maybe 50 square millimeters that you can play in for $20,000, $30,000, and they'll send you some chips, right? And that may also work for your prototyping needs, for your R&D, even just as a company. Maybe you don't even need to partner. But at some point, if your volumes are large enough, that may not support what you need as a company, for example. So if you're not at this huge volume, but you're beyond sort of the prototyping volume, I think there's a gap there. And then if you want to bridge that gap, you still need some millions of dollars to tool to build the facility, and then you have to maintain that facility. And beyond that, you really need stellar reliability, which I think is non-negligible. Even if you had the money to build a fab, right? Keeping that working well is really important. And yeah, and also looking at more exotic materials. You know, if you do R&D, maybe those materials don't even exist in the multi-project wafer runs that you want to utilize. And so as the R&D pushes ahead and maybe the MPW hasn't caught up, there's even this gap as well, even at the small scale.
Yep. Chris, you want to add anything to that?
Yeah, I guess I would add that I think national labs can play a pretty unique role in the technology transition space. So, you know, we're really uniquely set up to do things like work with new materials, develop custom processes, and work with people in the early prototyping stage. You know, our fabs work on what we call a low volume, high work mix capacity. And so we're used to working with new and kind of unusual things. And so that's really a nice opportunity for small startups, individual researchers and PIs to collaborate with us on. And then, you know, we do have some pretty good success stories transitioning technology to external partners and commercial entities as well. And so I think we'd be very happy to work with companies to do tech transition once it moves beyond the research prototyping stage. And so then that requires, though, getting another commercial entity invested in doing that transition with us.
Well, I mean, it's kind of curious to know, right? A lot of people probably didn't know this, but you are a leading ion trap supplier to the ecosystem today, right, for quantum computing.
Yeah, so right now, Sandia is one of, you know, the few places that makes multi-metal level surface ion traps, and we kind of do a service to the community and supply those to researchers. And for many years, that activity has been funded from IARPA. So IARPA has funded us for many years to support their programs. We've fabricated many ion traps, and IARPA has been kind enough to allow us to supply those to researchers throughout the world. You know, we're not making any profit off that. We're just, you know, helping the community out.
Yep. Yeah, great. William, you have anything to add to that?
I think, you know, both Chris and Jen covered most of it, but I would maybe stress that there is actually a, you know, kind of like a significant challenge. Once you've demonstrated the prototype, how do you actually manufacture it kind of large scale? And there aren't, because of how many materials, it's not kind of like the, you know, silicon foundries where it's just silicon, germanium, and maybe some other materials. Photonics, there's all sorts of materials out there for different wavelengths, for different, you know.
So give us an example of all the materials you're using right now.
Yeah, for instance, indium phosphide, gallium arsenide, lithium niobate, you know, silicon nitride, silicon dioxide, of course. And there's different materials for active, passive, modulation. You know, second harmonic generation requires materials, polling. So because of that, and it's evolving too, right? It's not just staying constant. As people develop new materials to do, and we're still missing capabilities, that needs to be incorporated into the clean room. So it's kind of an evolving process, and some critical need is missing here.
Yeah, so to build on that, right, so you also have, both Sandia and Lincoln have a very advanced semiconductor tools, $100 million tools type of thing, right? So in terms of like gaps, the commercial ecosystem sort of needs that, right?
That's right, yeah.
And so that's something that for funders out there, that's something, I mean, would you agree that that's something that the ecosystem is going to need?
Exactly. Once these things become, you know, mature to very mature, you know, once we want to really, you know, large scale manufacture these chips, that's just not really a good system in place for that right now. I guess the question is on timing, when that should occur. And it should be sometime in the near future, I would just say, yeah.
No, great, okay. So it's getting later in the day. Let's make this a little more interesting. So, Chris, you know, let's start with you. So what is the most exciting thing you've worked on with photonic integrated circuits in the last year that you can share publicly?
Okay. I'm going to say two things. One, without picks, just so I don't get.
Yeah, that's fine. Go ahead. Yeah.
So we have a quantum computing test bed called QScout, and so that's funded by DOE Office of Science, where we make small scale open quantum computers, and so anyone can be a user of that system. You can write a proposal and work with us, and so that's a really cool and interesting project. It's not ready for PICs yet, you know, because PICs aren't ready, ready to be incorporated into testbed level systems. So there's work to do there, and that motivates a lot of the PIC work that we do. We have another program called the Quantum Systems Accelerator, and that's NQI Center. In that program, we've been trying to push, moving beyond NISC quantum devices, and we're starting to look at things like photonic integrated circuits on chip, acousto-optical type modulators, and their associated waveguides and things like that.
Yeah, great. William?
I would maybe add two more exciting things I personally work on and I'm very interested in. One is narrow line with lasers on chip. It sounds easy. Lots of people are in it. But as you scale, bulky systems down, especially when you get on chip and into waveguide material, the refractive index just changes from anything. The window passes by, the refractive index has changed so that your laser shifted about 1 gigahertz. Now, if you're trying to target an optical atomic clock where your transition's on level of hertz, you need like a nano-Kelvin stability. So that's been very challenging. We have the narrowest line width laser in the world on chip right now, but even then, that's just barely able to address this. And it took a lot of design and engineering to get it to that level. The second thing I'm very interested in is actually lithium niobate. Now, this is kind of like a very hyped up topic right now, but I think there's actually good reason for that. And the reason is actually because as you confine things down into smaller and smaller volumes, usually going on chip, things get worse. It gets harder. Lithium niobate is the opposite. I mean, it's hard, but there's actually a lot of benefits.
It's an understatement.
It's actually very hard, but when you confine light down to small volumes, all of a sudden the intensity just blows up. And things that, like nonlinear optics, second harmonic generation, all becomes accessible with milliwatts of power now. And also, you can put your electrodes very close, and so modular V-pi's go down. So those are the two topics I would pick.
Yeah, great. Jen?
Yeah, so the most exciting thing I've worked on is funded basically through DARPA MTO, and it's very much along the lines of what you're talking about, which is to shrink down basically optical gain and modulators and laser sources, but for visible wavelengths. And this doesn't have to be for quantum, but it's very relevant for quantum, and it's critical. These types of technologies like the clocks and traps and things, all these large-scale systems, if you go look at them in the lab, they may be compact through certain programs. But if you look on the optical table we were talking about earlier, you see these gigantic lasers, and many of them use nonlinear wavelength conversion. They take nice, stable, near-infrared lasers, and they scoot them to these strange, relatively new in the world of commercialization, at least, wavelengths. And they need to be really good quality. And so I worked in the DARPA program where we were trying to shrink these types of devices to access laser wavelengths in the visible. And we were also employing, for example, lithium niobate, which is an active material. Because one of the dirty secrets in integrated photonics is that once you fabricate it, you can't really tune, like if it's a dielectric, it's a passive. So some people will etch them after the fact or do all sorts of things. You can maybe heat them to move their properties a bit. But things like lithium niobate are actives, and so they give you functionality that you can't get with something like a silicon nitride. So anyways, we looked at these sorts of platforms using parametric gain to access wavelengths in the visible and combine multiple materials, which is a real technological challenge, real cutting edge R&D, and not something that's available in sort of commercial foundries. But I imagine, yeah, you were mentioning lithium niobate has a lot of hype, and I think that that'll be one of the materials that I think as a community we're converging on is rather important for a number of reasons. Yeah, to be determined what other materials are acceptable or accepted in the community to the point of being available commercially.
Yeah, and it's funny because lithium niobate had its big run, died down,
exactly.
big run, and now it's coming back again. So, but now I want to go, so we just talked about the past. Let's talk about Chris, what are you excited about now? What do you see? So we're talking a lot about where this is all at, where the gaps, where the funding has been very helpful, but where do you see the excitement now for yourself in picks for quantum or quantum picks moving forward?
Yeah, I think it's an exciting time for photonic integrated circuits, especially for quantum, because this optical table picture, we haven't really gotten there yet, and I think we're right on the precipice of doing some interesting things there. And so really going to high density optics that are supporting large quantum systems is something that I'm excited about in the future. And what that's going to lead to is a number of challenges that we still need to address. One, heterogeneous integration, that's what we just heard a lot about, is in quantum, it's not just low size and weight and power that's king, it's really performance. And so you're going to end up most likely with the most performant components of a bunch of different material systems in your pick. And so you're going to need to figure out how to integrate a bunch of different materials in a way that's also low loss, because these quantum systems are power hungry and also starved for photons, and so you can't tolerate a lot of loss in that. And then finally, there's a packaging challenge when we go to these very dense quantum systems, is how do we get many different fibers onto a chip? How do we get many different fibers into a vacuum system, for example? Those are some of the challenges I see and some of the things I'm excited to move forward.
Yeah, great. William?
I would say I'm most excited for like the measurement capability offered by quantum sensors. I think, if you're familiar with how a frequency cone works, that's one of the most magical things in the world to me. And nothing,
Not just you, right? Yeah. People, yeah.
It has both breadth and also precision at the same time. So, you can measure things down to 10⁻18 by down converting an optical clock, and you convert it to every single color that you would need. And that should open the door to any type of measurement you need. With that kind of precision, you can, measure fundamental constant changes, things like not only in fundamental physics, but maybe can GPS be enhanced? Can you measure something down to centimeter precision or below? Can you track an ant on the floor or something? Yeah, so it seems very exciting, the measurement capabilities.
Yeah, great. Jen?
Yeah, I agree. I think I love the physics and the technology in developing all those ideas, but it does promise, these technologies promise a lot of interesting devices, from metrology to quantum applications, and I'm excited to see these things actually come out of the lab and to go into devices, and maybe that'll be into larger photonic systems at first, not a full pick maybe, but seeing especially like a nonlinearity, picks are really great. They're well suited for these types of applications. They have unparalleled nonlinearity compared to like other photonic systems. And I'm excited to see the low swap enabling these really cool experiments to come out of the lab, to go into the world, and for them to be affordable, and to make the types of technologies we're hearing about at this conference accessible. But I also think that funding these picks for quantum is also going to enable a lot of other technologies that maybe are not so quantum, but it'll enable lots of different technologies within and outside of quantum.
Yeah, great. Any wild card questions from the audience?
Yes. Actually, in terms of commercial foundry, my company does offer a thing called lithium niobate. But the question that we often...
And your company is?
Yeah.
Quantum computing.
Yeah.
Okay.
Just want everybody else to know. Yeah.
The question that we often receive, and Chris, you alluded to that a little bit, was on the packaging solutions. And my question is,
Yeah.
for the quantum application, what sort of packaging and assembly do you foresee that will be the winner? You mentioned the heterogeneous integration, but that's not the only one. So what is your perspective on that? Which solution do you think would have more?
Oh man, I think it's still TBD and it needs a bunch more research. I don't think I can pick a winner at this point. Sorry.
William?
Yeah, I don't know. I think we're still a little bit ways away from trying to package everything up. I'm still not even sure if the active material should go on the passive material on a single chip, and whether it's better to separate the two, because the heat load might just be too much. So that's something I still don't know yet. Yeah.
What about, like, there's different, when I talk to many experts in the field, some of them are going homogeneous, right? So maybe it's easier for them. Who knows?
Yeah, exactly, yeah.
Right. Okay.
Yeah, I also don't know the packaging answer, but that is interesting also from the heterogeneous integration perspective. And like heat is one thing we didn't talk about. It's a real technical challenge. And also, especially for quantum, we're talking about the losses, right? And maybe even you get the losses perfect on chip, but then you go off the chip and, what are you suffering there? Even 1 dB maybe is not acceptable. And so I think there's a lot of work to do there. Yeah, not sure.
And it's clear, right?
Yeah.
Because it's maybe not so clear for everyone in the audience, but You've got picks that control quantum effects, and then you have PICs that are managing quantum signals. And when you're managing a quantum signal, like what Jen's talking about, or what they're all talking about, is if you hit loss, you may lose your single photon.
Right.
It's gone.
Yeah, and even for the visible applications, you might want a lot of light to go to your atoms, your ion, right? So similar problems, though, for different reasons. These are PICs for quantum and quantum PICs, I would say. I'd be happy to talk to you more later.
We're out.
All right.
Perfectly on time.
There we go.
Thank you so much. I appreciate it.
Thanks, man.
Effort.